Hello everyone, welcome to this session. I'm going to present a system called SOTERIA, which is a provable and transparent user right management system using a novel two-level blockchain technology. And we all understand privacy is critical for all the users. In the internet era, powered by artificial intelligence, all the algorithms doing inferencing, ranking, recommendations require a large number of user private data. And in the past few years, there have been some scandals. For example, the Facebook Cambridge Analytical scandal, and also recently, both YouTube and Google were heavily fined for the violation of either GDPR or CCPA. So in today's presentation, I'm going to first outline the representative privacy regulations, and then I will discuss how to be in compliance by implementing a system. Then we get into the architecture of SOTERIA, discussing the multi-layer blockchain, the trade-offs between consistency and the performance. And finally, we discuss a very critical element which is called digital contract, which encodes the agreement between a user and the data custodian, and how the contract can be formulated first in natural language, converted automatically to a piece of code, and later we can use SMT to automatically verifying whether a piece of SQL code is in compliance to the digital contractual agreement. Let's start by defining some critical terms. And three key regulations, including GDPR, which is the privacy regulation produced by EU. The second one is CCPA, California Consumer Privacy Act, initiated at California and put into practice early this year. And we believe this CCPA will be adopted by other states in the US quickly. And finally, HIPAA is a set of regulations specialized in the healthcare domain. And we will be using the term data subject frequently, which represents any person whose data is being held, collected, and processed. Another term, personal information or PI, is defined by CCPA or GDPR as the information which can be utilized to identify a person, either directly or indirectly. Directly, for example, your social security number, and indirectly, for instance, your address plus your profession and the gender. And even your family may have a lot of people. By using those information, we could zoom into one individual. Even we have multiple regulations, privacy regulations. Their main spirit is pretty much the same and can be summarized into the following Bill of Rights. The first one is right to consent to be collected, the data to be collected, and right to be informed when the data is being processed or shared, and right to access one's own data, right to erase your private data and to be forgotten, and right to data portability, for instance, moving my data from one hospital to another. And then finally, right to rectification, changing my data information. And the agreement or the rights can be preserved by between the data subject and the data custodian signing a contract. The contract, of course, the traditional contract is writing on paper, but in our case, it's a digital contract. The digital contract is written in natural language, covering what data to be collected, how data will be used, and what the user will receive as an exchange. This is a very interesting topic we can address separately in the future. And will the data be shared and shared with whom? And finally, you can have other customized fields depending on the regulations. In the second stage, I'm going to talk about the compliance requirement, how we can implement those requirements. And the first implementation requirement is we keep indelible records for all data transactions processed on the contract. Okay, so the first transaction, of course, is a contract agreement, and we can have contract revocation or contract modification. And based on the contract, the person or the company can access the data based on all the agreements. And then implementation must ensure the transactions exhibit the same order, right? Because when there's any dispute, so we have this consistent order, we can prove the faults. And finally, we want to make all the transactions, but not the data, on this public ledger. And if you consider like Bitcoin, the data is actually in the public. But for privacy preservation, we cannot put a medical record or X-ray directly on the blockchain. So before we get into our implementation details, I'd like to review an important distributed system theorem called CAP, which is developed by Eric Brewer, a Berkeley professor in year 2000. So basically, the CAP theorem consists of three properties. C stands for consistency, A, availability, and P, partition tolerant. And the theory states only 2 out of 3 properties can be simultaneously ensured. So either when we build a distributed system, we pick either CP, AP, or CA, but not all together. But our aim to preserve privacy, we want to have a CAP system. And shortly, I will tell you how our system is designed to achieve all 3, right? And the most famous distributed system is Bitcoin. And Bitcoin picks A and P. A, they would like to be up all the time, so all the users can do their trading. And partition tolerant, again, they don't want anyone's system shut down to affect other people's operations. And at the same time, they have to trade off consistency. And we know that's exactly the shortcoming of the Bitcoin architecture. And instead of using the efficient protocol, they have to be able to get consensus from a large number of users. And you know, the cost of maintaining such an infrastructure is very costly, and the cost for solving the so-called puzzles also very costly because of power consumption. And more seriously, the system suffers from low throughput. Like Bitcoin transaction per second is about 7, then Ethereum maybe about 15. And the latency is quite long, up to 1 hour for the system to reach global consistency. And I mentioned already, it also lacks privacy because you pretty much just put your transaction content or the data on the chain. So the second kind of system, also very popular, is centralized. The banking system, airline reservation systems, they are all centralized. If any computer within the system is problematic, then the company just shut down the entire system. For instance, like an ATM machine, if you deposit money into an account and then withdraw from the same account, they have to make sure the money is in before you can withdraw. So consistency must be strongly guaranteed. At the same time, when the system is up and running, availability or the throughput must be very high. And for a centralized system, it enjoys some pros and at the same time also suffer from some disadvantages. The benefits are high throughput. That's great. That's what we really want. And low latency, less than 10 seconds. When you walk up to an ATM, you don't want to delay to be minutes or even an hour. It's impossible. And for its shortcomings, first of all, it's not decentralized. So it's not transparent. So therefore, it's not suitable to our purpose to have a provable and transparent ledger. And there's no privacy again. Data may be stored on the chain. So using different consensus protocols enjoys the approach, maybe high safety, but has to suffer from some cons. There's no free lunch. And we cannot say which consensus protocol is the best. We can only say which consensus protocol is the most appropriate under the situation. So let's just quickly look at 5 families of consensus protocols and their trade-offs. And we know about Bitcoin using POW, proof of work, and which is very expensive, but it's permissionless. Anybody can join without need to go through validation and sign in. And it's not trusted. And scalability is very good because everybody can just join the system. And the transaction rate, as I already mentioned, is low. And proof of stake basically say, well, you can pretty much weighting the power of work. It's power of work plus some kind of weighting scheme. And the performance is improved. But still, the throughput is not extremely attractive. On the other end of the spectrum is to support this kind of C and A system, consistency and availability. And like a BFT system and the federated BFT, and someone may call practical BFT system. And those systems typically can be permissionless, and they can be permission. And the transaction rate typically is very high because they only require a small number of participants to reach consensus, so they can commit the transaction. In healthcare, as an example, suppose I would like to secure consistency for particular transactions, then I could have just a limited number of people to participate in the validation phase. And this limited number of people is called jury, right? My jury pool could consist of a number of trusted hospitals and maybe plus some trusted nonprofit organizations. And at the same time, maybe sampling some users. In such a way, because the number of participants is much smaller compared with something like Bitcoin need to support millions of people. So the number of messaging, even the complexity is O to the power, O n to the power 2 or n to the power 3. But since n can be quite small, between 10 to 20, its throughput and latency can enjoy good performance. Now we understand these high-level spirits of different consensus protocols, and we would like to achieve CAP property. But we know we cannot achieve all 3 at the same time. But how about splitting our ledger into multiple layers? And the base layer of SOTERIA can support like the decentralized system, guarantee AMP, just like Bitcoin. And our secondary layer, or we call sidechains, support CA. In this way, if we look at our 3 layers, the top layer is a public chain. It enjoys decentralization, so all the users can perform auditing. It's transparent to the public. The second layer is permissioned. It's a CA properties will be guaranteed. And it can run high throughput, low latency consensus protocol. So the second layer, let's say a side chain, and after every n transactions, and or we filled up a particular block. Then we hash the root of the block, or you can say the root of the Merkle tree onto the first layer. All right, so in this way, after n transactions, we involve the base layer transaction only once. If n is equal to 1,000, in effect, we are improving the throughput by 1,000 folds. This is the way the key spirit, this multi-layer architecture, can improve throughput and enjoy low latency. And even more interestingly, suppose every sidechain has, let's say, 20 seconds to 30 second latency. And we say we want to further improving throughput from, let's say, 10,000 to 30,000. We can simply just replicate sidechains. Of course, there are some properties need to be ensured, and we can discuss it offline. The final layer of our multi-layer SOTERIA architecture stores digital contracts, which we will revisit in a few slides. Let's now evaluate the performance of different protocols on our sidechains. After survey a number of papers, there are 4 representative protocols can serve well for a CA system. These 4 protocols are Tendermint, Stellar, Hot Stuff, and Hashgraph. And on paper, each protocol publishes their performance according to their own configurations. So the table here is not really conducting an apple-to-apple comparison. And on paper, we could see Hashgraph performs the best with highest throughput. However, since we cannot get a hold of a reliable open source implementation, and we pick Tendermint and Stellar to conduct our further experiment. And we configure them on the equivalent systems, and then using throughput as the input and measure output either throughput or latency. And in this figure, the left-hand side shows throughput can be achieved versus the input rate. And input rate up to about 400 to 500, all the input can be serviced without any problem. Beyond 500, the system capacity may be saturated. And we can see that the Tendermint performs better than Stellar. On the right-hand side shows the latency performance. In the Tendermint configuration, it also enjoys lower latency. And we talked to the co-founder of Stellar, and he expresses that it's not very hard to improve the Stellar system if we know how to tune the internal parameters. But in any rate, we consider both protocols to be suitable. And if different entities like to use different sidechains, our architecture can tolerate heterogeneous sidechains. And the next picture shows a similar evaluation, and which shows that with about 16 to 32 nodes, and our system can support about 300 transactions per second under 50 seconds of latency. And 50 seconds looks pretty high for an application like payment, but for privacy auditing, a user typically wouldn't do auditing task within a few minutes. So 50 seconds is very reasonable for our targeted task. Let's look at our architecture in more details. First of all, let's look at the user interface. On the left-hand side of our SOTERIA system, we see this user right management system, which is the interface allows data subject to negotiate a contract with data custodian. And for instance, you may have multiple choices, allow each party to click on and to approve. And maybe a pricing agreement can be reached. once the agreement has been reached, then the agreement will be stored on the sidechain. And another service on the left-hand side is audit trail service. The purpose is to cache the transaction information on the sidechain on this server, so to provide quick access and quick search. And at the same time, this caching service has points to the real record stored on the sidechain. So therefore, when we want to search for a particular record for auditing, we don't have to do a sequential search on the blockchain. We can go through the service to quickly find out the location of the record on a sidechain. And I've mentioned this is our sidechains, and sidechains would periodically hash the root of a block onto the main chain. And our choice of main chain is Ethereum. And between the sidechain and the main chain, there's a performance parameter, is the update frequency. We talk about update every time we filled out a block on the sidechain, then we update the root hash of the Merkle tree onto the main chain. So suppose the number of blocks per fingerprint, let's say, is 20 versus 50, we like to know the impact of the update rate to the overall system latency. Unfortunately, from the experiment, we can see the overall latency is quite stable between about 23 seconds to 50 seconds. On the sidechain, it's very low, right? It's consistently below 10 seconds. However, the main chain, we know the main chain like Ethereum and Bitcoin may suffer from much longer latency. And it's virtually impossible for the sidechain to time the main chain to submit the update, so therefore minimize the latency. It's kind of stochastic. But in average, the overall throughput and the latency can be reasonable, as we have explained. And we have discussed about the first two layers of our SOTERIA architecture. The final layer is this natural language digital contract. And we store natural language on the contract on the blockchain because then anybody can understand the content of the contract. If we store the code onto the contract, then it's virtually impossible for most people to audit. So we are using Stanford Oval ThingTalk as our low-level language. And this is an example showing the statement on the top, gamma pi RMP, and R is a consumer or data subject, and the P is the data custodian. Then there are fields like F1, F2, and those are permitted for the data custodian to access or process. So using this ThingTalk, you basically can convey what fields of the data will be shared between the custodian and the data subject. And the second element is to perform verification. Before saying that, let me give you an example of the language conversion to the code. So suppose our contract is written as Stanford Medical Center can read the age, ethnicity, and the PSA of Bob's electrical health record for research. And if the PSA is greater than or equal to 2. So this scenario may be on an IoT, which constantly measure the PSA of a patient, Bob. And this natural language contract is written to the following code. R is equal to Bob, gamma is equal to Bob, R is equal to Stanford Medical Center, and the P is research, and the fields allowed to be accessed, including age, ethnic, and the PSA. The condition is the PSA has to be greater or equal to 2. Okay. It is critical to be able to verify the code written to access user data is in compliance with the sharing agreement signed between the data subject and the data custodian. In this example, we show a SQL statement on the top. Then we have the agreement between two parties. And we use SMT, which stands for Satisfiability Module Theory, to generate a set of conditions. And if that set of conditions is satisfied, then we know the code is in compliance. In closing, today I presented SOTERIA, our two-tier blockchain architecture for safeguarding user privacy in a provable manner and also transparent. And I'd like to acknowledge my co-authors and collaborators. Thank you so much for your attention.